Today, I'm going to give a talk on equivalence testing and applications that I think would be particularly useful in the DoD in general and test and evaluation. I think as you'll see in this talk, equivalence testing isn't really a complicated analysis method. It's pretty straightforward, but I haven't seen it used very much in the DoD or in T&E. And so I want to kind of highlight some examples where I think it could be useful and kind of give you some insight on it. Okay, so quick outline of the talk, go through the difference between, sort of traditional hypothesis testing versus equivalence testing, show just a couple two notional examples to give you an idea of how it could be used, and then end with some specific considerations you have to take into account if you're going to use this method. All right, so why equivalence testing? Well, imagine a couple different scenarios that perhaps you've been in. So I know there's an M&S session, here at DataWorks. So imagine you have done a model, you've created a model for your system, and you've collected some live test data, and you need to validate that model. Well, ideally, what you'd want to do, right, is confirm that the results from your model or your simulation are the same or similar or equivalent to the test data, the real data of your system, right? That's the whole point of model validation. So your objective of that kind of data collection is, I want to confirm the results, right, are similar in both ways I've collected the data. Another example I've seen recently, you have a training program, right? You're going to train operators on a certain system or a certain technique, and you've updated that training program. Maybe there's a new syllabus, okay? And you want to, the new syllabus allows you to, I don't know, make it shorter, streamline how you teach things. And now you want to see or prove that this updated training program hasn't affected the performance of your trainees, your operators, right? Suppose that you switch out a part or you switch components in your system, right? Maybe it was cheaper, or you've gotten an upgrade, and you need to show that the performance of your overall system hasn't been negatively impacted or affected by the performance, by the change in that system. And Brian, this last example is not DoD related at all, right? Suppose you are, creating a new drug for the market, for some disease. You've got a generic drug, it's going to replace a brand name drug. And you have to show that it's equivalent. I highlight that last example because equivalence testing is already really commonly used in biostatistics. The FDA has requirements when a generic drug manufacturer is going to add a drug to the market. It has to prove statistically that the performance of this drug is equivalent to whatever's already on the market. Okay, so what's similar in each of these different kind of scenarios is that the goal, the objective of the data collection is you have to prove that there has been no change, right? There's no difference, right? That's a little different than what we typically think about if we're going to do a traditional hypothesis test. All right, so let's just think about a two sample t-test, right? And let's use, I'm comparing two different populations for the purposes of this talk. There are other variations I'll mention at the end of the talk, right? Null hypothesis, my group means, right, are the same, equal to each other. My alternative hypothesis, they're different in some way, right? So I collect the data, do the data analysis, I get my two sample t-test all set up, and I can come to two possible conclusions based on my data collection, right? One, calculate the p-value. If it's less than or equal to my significance level, less than alpha, right? I reject the null hypothesis and conclude, hey, the two means from these populations are different, not the same. Right? All other possible decision you could make, the p-value is actually greater than the significance level, right? Greater than alpha. So does that mean we can conclude that the means are the same? Well, no, we have to use our nice, lovely statistical, logic here. Well, we just fail to reject the null hypothesis, right? It doesn't mean that they're the same, but we just don't have evidence to conclude that the means are different. Right? But if you're in one of the scenarios on that previous slide that I talked about, right, you really want to prove that the means are the same, right? So if you're failing to reject the null hypothesis, that's not really a very strong conclusion at all. You're not really matching the analysis to the objective of your test, right? So think about, what conclusion do you really want to make when you're collecting data? Do you want to show things are similar to each other, or do you really want to show that they're different, right? So in all the cases I've talked about, we want to show, prove, conclude that they are the same. So a t-test isn't really the appropriate statistical method to do that. So what can we do? Well, why don't we just flip the hypotheses, right? That's the notion of an equivalence test. If we really want to show that two means are similar to each other, failing to reject the null hypothesis isn't really the right way to go, right? It's not a strong conclusion, right? So an equivalence test, literally you flip the hypotheses. So rather than initially assume the means are equal to each other, and the alternative is that they're not equal, we'll initially assume these two means not the same, they're different, and we want to conclude that they are the same. Okay, now in actuality, it won't be exactly equal to each other. You'd need like sample size to infinity to ever show two continuous means, right, are the exact same value. So we'll talk about some of the considerations there, but that's the idea of the hypothesis test, right? You collect the data, do the testing, right? And if you reject the null hypothesis in an equivalence test scenario, now you've concluded, hey, these two population averages are essentially the same. Okay, much stronger conclusion if that's what you're trying to prove. All right, but yeah, you can't just say that they're exactly equal, right? Statistics isn't magic like that, if only, right? So how do we define what is close enough, right? How close is close enough to be considered the same, right? So this is where you have to pull in a little bit more subject matter expertise to determine this. So we'll initially assume that the means are different, and in fact that they're greater than some value delta. This is called the equivalence acceptance criterion, right, denoted by delta here. All right, so our null hypothesis will actually be that the difference between these two means is greater than some value delta. And the alternative is that it's within delta. That difference is within delta. So we kind of have it shown here as a picture. The green region represents our alternative hypothesis, the difference between these means within minus delta, positive delta. And the null hypothesis is in this blue region here. Okay, now, in theory, you don't have to have this be equal sided, right? So you could put in, say, delta 1, delta 2. But for the purposes of the method that you typically use for this, it's more straightforward to have it be sort of an equidistant value for delta. So that's what we use in this talk and in the methods that I show. Right. So then how do you actually do the analysis? Well, again, like I said, this is a straightforward method, right? It's not that complicated. Where your null hypothesis can be broken out into, or your hypotheses can be broken out into two statements. So in the first one, we have our difference in the means is less than or equal to minus delta. The alternative, it's greater than minus delta. And we do a second hypothesis test looking at the difference, is it greater than positive delta, and the alternative being less than delta, right? So this is just matching up our two regions here. So if we reject the null hypothesis in both of those hypothesis tests, that means that we're showing that we are in this green region here, in the alternative hypothesis region. Okay, this is called the two one-sided test approach to equivalence testing. And because this is the DoD, we give it an acronym called TOAST. And so this is the really common way to do equivalence testing. And so you have to do both hypothesis tests, okay, to conclude equivalence. So if both null hypotheses are rejected, then the population means are considered practically equivalent, okay? If only one or none of them are rejected, then the two means may not be equivalent. So again, we can't say that they're different, right? Because we're just failing to reject the null hypothesis, right? So it just means that, well, we can't conclude statistically that they are equivalent to each other. All right, another way to look at it, you can always calculate a confidence interval on the difference between the two means, right? So if you're doing the two one-sided test approach or the TOAST approach for equivalence testing, you can calculate a 100 1 minus 2 alpha confidence interval on the difference between these means. And if that confidence interval lies between your equivalence criterion region, so negative delta to delta, then that is the same as rejecting both one-sided tests. So you could conclude equivalence, right? So of note though, the confidence interval is an alpha size test. So if I'm using a 5% significance level, my confidence interval would be a 90% confidence interval on the difference, but that equates to testing for 5% significance level in the equivalence test, right? Because we have to do the two one-tailed tests. right? This slide here kind of shows the relationship of where you could end up between hypothesis test and equivalence test. This figure is actually from a paper in Quality Progress from about 15 years ago, which I really like the visual. So what do we have here? Each vertical line, kind of 4 different scenarios. The vertical lines in each case represents traditional confidence interval. So let's say it's a 95% confidence interval of the difference between 2 means. Okay, so if we were going to try to do a traditional 2-sample t-test and we want to determine is there a difference, right, between our 2 group means, right, we can calculate the 95% confidence interval, and if it doesn't overlap, say 0, which is our equivalent line here, then we would conclude that they're different. So that's what we see in these first 2 cases. In these 2 cases, the 95% confidence interval, again, the vertical lines overlap the sort of the equivalent line, right? So we can't say that they're different. The hash marks, or these kind of horizontal lines overlapping the vertical lines, represent a 90% confidence interval, okay, between our 2 means, which would represent, if we were to do an equivalence test, right, we would need our vertical line interval to not cross any of the critical regions, so the minus critical or plus critical, right? So that sort of represents the deltas that we talked about, right? So in these first and last cases, right, the equivalence confidence interval here overlaps our critical region, so we would not conclude equivalence, but in the middle 2, right, it stays within our critical bounds, so is equivalent. Right, so you could have these different scenarios occur with the same data, depending on what your value of sample sizes and noise and the actual effect size. Right, so I kind of like to look at these second and fourth cases, second and last cases, right? So I could have a case where I see a statistical difference, right? But it's so small it doesn't have a practical impact on my system, right? So we see that if with very high-powered tests in DOE, for example, right? I did detect a statistical difference, but it's not going to affect my performance or the mission operation anyway. Right, this last case is sort of like, I can't show that they're different or that they're equivalent, most likely because the noise is incredibly large or you just don't have enough data. It's a low power test. Okay, so that's sort of the behind the scenes. Didn't show the math because we can use software to do most of it for us. But again, it's just some one-sided tests. So let me show a couple examples to give you an idea of how this could be used. These examples are notional, but you know, realistic enough, right, to show potential applications. So mentioned model validation before. So let's suppose we have some weapon system. They've developed a model and they're estimating the miss distance. Then they execute some live testing in some, you know, field or arena, whatever, and they want to compare it to the model results and show that, hey, our model and the live data are matching. And so maybe now we can use the model instead of trying to spend money and collect more data. So we talk with some subject matter experts, the operators, and they say, well, if there's a difference of, say, 5 meters, that wouldn't have an operational impact for this particular system. Okay, and so that becomes our equivalence acceptance criterion. That's our delta value. Okay, so again, data is notional, but here's just an idea, right? I have my null hypotheses. I want to see, is the mean between the model and the live data, is it less than 5 or is it greater than 5? And then my alternative hypothesis is that needs to be, the difference needs to be between -5 and +5. All right, so here's a kind of visualization of the data. Again, and we see, well, the live test data looks to see like it's not performing quite as well as our model said it would, and maybe a little bit noisier, just a little, perhaps. So our observed difference is actually about 4.4 meters, which is under our delta, right? It's under 5, but now we got to account for noise and all of that, right? So we do our equivalence test, and we have to do both one-sided tests, right? So our lower bound p-value, again, that's comparing against the -5, or is it greater than -5, right? So that p-value is very small, right? If we're using alpha 0.05, we'd reject that null hypothesis, right? But our upper bound p-value, so this would be comparing, is the difference greater than 5 or less than or equal to 5? And that p-value is quite large in this case, right? It's almost 0.3. So we would fail to reject the null hypothesis in that case, right? So if we want to show equivalence, that the difference between our live and live and model data are within 5 meters, right? Well, we can't do that, right? So we can't conclude that our model and live test results are practically equivalent in this case. And here's the 90% confidence interval of the difference between the means. And we see that upper bound is about 6.3, which is greater than +5, which is our delta value. Okay, so one example where, well, yeah, we can't show equivalence for this one. Okay, one other example. This was the training example I mentioned. So we've got a program, it's implemented a new training syllabus, and they want to confirm that the new syllabus hasn't negatively affected student performance. So in this scenario, let's just suppose they do some sort of, final test or score to measure achievement after training, and it's measured on a scale of 0 to 100. And the instructors determine that, well, if the scores are within 10, that's good enough, right? So again, close enough. We'll talk about what close enough really means, right? What, in this case, 10, good enough. They'll be able to accomplish the mission, use the system with no issues. So again, here's our data. We've got the training A, that was sort of the previous syllabus. Training B, it's an independent set of students. They went through a new syllabus, but took, same kind of final test, got the score. They look pretty similar. The observed difference is about 2 points. So that's looking pretty good, right? So we do our one-sided tests for both sides, the lower and upper bound. P-values quite small. So we would reject the null hypothesis, right? The max p-value between both of these tests is well less than a significance level of 0.05. So yes, now we conclude that the mean training scores are practically the same for both syllabi using that acceptance criterion of 10 points. Okay, and we see that the confidence bounds using 90% confidence here, this interval lies within -10 and +10. So again, statistically equivalent. All right, if we had done a 2-sample t-test comparing these two, the p-value for that test is greater than 0.05, right? So you would fail to reject that the null hypothesis, fail to reject that the means are different. I'm sorry, fail to reject that the means are the same, right? But that doesn't actually conclude that they're the same, right? The equivalence test actually allows us to say that. And so that provides that stronger conclusion for our new training system. Okay. So again, not a complicated method. You can do the 2 one-sided tests. Actually, it's available in JUMP if you want to do an equivalence test. In JUMP 15 and 16, I believe it's available. If you want to use R, there is a package called Toaster, Toster, available that implements equivalence tests. So it's pretty easy to implement in practice, actually. But there's a few considerations that you have to take into account. Of course, nothing is free. Okay, so we've talked about the delta value, your equivalence acceptance criterion, right? So that is an input that you have to give when you're doing this analysis, right? You don't have to do this for a 2-sample t-test. You might use it to plan, right, and to estimate power and things like that, but you don't actually have to specify it in the actual analysis. Right. So delta is the value or the level at which the population means are considered close enough to be acceptable. Right. So as a statistician, I can't tell you what this number is, right? I don't know what your system is, right? I don't have insight in how close is close enough for your particular operation or your mission. So you really have to get this from subject matter experts or operators, the decision makers. It's not something that's just going to be lying around. If you're just like, oh, here's our value for delta, we'll use that. In the FDA, if you're going to compare drugs and do equivalence testing, there actually are regulatory guidelines for comparing 2 drugs with efficacy and toxicity and those types of things. But for industry and kind of DoD applications, yeah, there aren't any regulatory guidelines for this. So you have to rely on subject matter expertise for this. If there's such limited information, a common technique that you could use is say, well, you're going to consider that the 2 means are equivalent if they're within some % difference from, say, your control group or your group 1. A couple papers I read said, 5 to 20%. The 20% seems quite high to me, but again, it's very subject dependent. So if that works for your system or for your environment, just you need to have an agreed upon value for it. So here's sort of again that picture of, how far is delta away from our difference between means. So is sort of this medium-sized difference good enough? Does it need to be quite small to be considered equivalent? Or could you go to some extremes? Hey, if they're within very large distances, that's considered good enough for me, right? The big part though is that this has to be agreed upon prior to data analysis, right? Don't play the game, right? Of I'm going to do the test with some value. I don't like the results, so let me redo it and change the value for delta, right? That's not the point of this technique. The point is always to make it match your decision, right? If these values, if these averages are within this range, then it's considered to be practically the same. It's not going to affect my operation, right, or my mission. Right, so you have to go to the SMEs, you have to talk to the decision makers, operators to agree upon this value really during the test planning period, right? And definitely prior to data analysis. Okay, here's an example of the effect of delta on the results. This is from, the figures are from JUMP. I did this analysis using JUMP. So this is for the training example, right? So in that example, I had delta set to 10. Okay, so here's the kind of figure representing this. And I won't go into all the details of these figures, but here's the basics, right? The boundaries of the shaded region represent the minus delta range, essentially. The dot represents our observed difference, which was about 2 in this case. So this is training score for one syllabus. Here it is for the other. It's about a difference of 2. And the line represents the 90% confidence interval between the means, essentially, right? That's the general idea. So if this line here lies within our delta region and the shaded region, then I can consider it equivalent. So if I change my delta to a different value, how that will affect our conclusions, right? So if in reality the students' means had to be really, really essentially the same, so maybe a difference of just 2, right? I would not conclude statistical equivalence, right? This confidence interval goes well outside that region, okay? And even if I set it to 5, it goes just outside the boundary. So again, I can't conclude statistical equivalence, right? So your choice of the value of delta will affect your decision. It's something that you have to think about, and you can't just blow off, right? You can't neglect it. It's an important value. It's essential to the method. So you have to really think about what is the appropriate value for this, and you need to talk to your subject matter experts and decide this is what makes sense for our system. Okay. And of course, you can't really ignore sample size and power, right? If you're doing test planning, right, traditional DOE or a t-test, you can estimate power and choose on the sample size, to achieve a certain level of power. So that's still important with equivalence testing. So you should perform power analysis to estimate sample size, or at least see how the amount of data, how well is it going to work with this type of method. So to calculate the power for the equivalence test, it's based on a non-central t distribution. It's pretty straightforward. I believe JUMP 16 has a sample size explorer for equivalence test. I will admit I didn't have JUMP 16, so I couldn't do that. But I believe it's available, which allows you to change these different parameters. I wrote a little function in R that does it for me. So if you want the little function, just shoot me a message. I'd be happy to share it with you. But you need a couple of planning values, right? You need your equivalence criterion. So that's the value of delta. You need to know what the actual difference between the group 1 and 2 means are. And of course, you need the estimates for noise for the group 1 and group 2 standard deviations there. And with all of this information, and of course your significance level, you can estimate power. So here I just did a very simple example where I just kind of messed with some of the, tune the different parameters. How would the power of my test change with different sample sizes and changing the standard deviations, my delta value, that equivalence acceptance criterion, and the actual observed difference, not the observed difference, but the actual difference should really be said there. I'll point out in this figure that the total sample size represents the sample size from group 1 and group 2, which ideally are close to the same value, right? They're about equal. right? So the green and blue lines represent these two cases here. So if I have very low noise, right, there's not a lot of variability, and the difference I want to detect, the equivalence criterion, right, is relatively small, pretty easy to prove statistical equivalence. The power is very high for small sample sizes here, right? So that's these two curves here, right? But what happens if I increase the noise, right, and hold everything else equal? So that's this blue line represented by case D, right? So it's going to take a lot more data, right? A lot higher number of runs to achieve a high power test. Okay. Similarly, if let's see, here's case E, right? The noise is about the same, but my observed difference, the actual difference isn't actually 0, it's 2, but I need to be able to show that it's within, say, plus or minus 5, right? That's also going to affect the power of the test. You need higher sample size to show the difference there, right? Or to show that they're the same. All right, so this is just an example of, it's still important to explore sensitivity of the power, all right, across the different planning values, okay, so that you're sure that the sample size matches the appropriate power for the test. I will say for equivalence testing, typically do need more test runs to show equivalence than to show that there is a difference. So, this might not always be possible to do in T&E when sample size is really restricted, but in cases where you can collect data, whether it's in a lab environment or the training example where you have a lot of operators going through training, this is a good method to show that things haven't changed, that they're close enough. Okay, I think I've only got about a couple minutes, so I won't stress these last couple slides here, but there are variations from equivalence. So for example, there are non-inferiority tests, which instead of just saying, I want to show that my results are within a practical difference, right? They're close enough on both sides. You could show, well, the results aren't worse, right? They're the same or better, but with the new group. And similarly, you can do the opposite side of that things are practically better with sort of your change. And so here's just some different variations of equivalence if you want to test a particular direction for that. So again, running short of time. So, the math is very, very simple. You're just doing a one-sided test essentially. Okay. I focused on comparing two independent means, in this talk. There are other applications, right? You can compare a single mean against a standard. You can compare a standard deviation against a standard, or two independent standard deviations. The one example that excites me the most, though, is comparing linear regression model coefficients. So consider our MNS example. Maybe you're testing your system across a set of factors, right? You do that in your model, you do it in the live test, and you want to show that the effect of each factor is about the same, practically the same, right, in both environments. So you can do an equivalence test on regression model coefficients, which I think makes a lot of sense in that sort of validation scenario. All right, so I think I'm just about out of time, but maybe time for one question. So again, there are applications for equivalence testing in test and evaluation. I don't see it used very often, so hopefully this might inspire you to think about using this technique in the future. So think about what decision you actually need to make. Do you need to show that they're different, or do you want to show that they're essentially the same? Right, but don't neglect the planning. Consider that value for delta, sample size, power, of course. And like I mentioned, you can do this type of analysis in JUMP, in R. There are analysis tools available to do this. So think about it, and let me know if you have any questions. Thank you guys so much.
All right, thank you very much, Sarah. We do have about 2 minutes, so we've got time for one question, and Dr. J was first up with his hand. So let's.
I'll make this quick.
Please.
Sarah, have you not considered using a Bayesian approach? Because in the frequency approach, both of those things you're looking at, those means are fixed constants. If you take a Bayesian approach on that, you can look at the knowledge of those as being uncertain and develop what's called a regional practical equivalence, which is described in Pressure book. I'm done.
Did you get that, Sarah?
So I think it was, could you use, did I think about using a Bayesian approach instead of the frequentist approach with equivalence test? And the answer is no, it did not to not do a Bayesian approach doesn't mean it's not valid. My biggest goal here was thinking about using the right analysis techniques for the decision you want to make, right? And so if you want to show two things are essentially the same, a standard two-sample t-test is probably not the right choice.
Same thing Krisky says in his book, and he introduces a region of practical equivalence and shows you how to do that with a Bayesian approach.
All right, well, we are at 11:20, so we are going to say thank you again, Sarah. We can all thank her.
Thank you, Sarah.
Thanks, y'all. Have a great time at DataWorks.